So far, we've looked at some really key concepts. That redox is electron transfer, that the loss of electrons is oxidation, the gain of electrons is reduction. We can represent those with half equations, and we can use oxidation numbers to show what species are being oxidized and what are being reduced. We've also looked at cell diagrams, and so the fact that we can generate an electrical current, electrical voltage with these chemical reactions. We've used electrode potentials to find out how big that voltage could be, or to show if something is spontaneous or not. All of that gets wrapped together with batteries. Batteries are an application, a real-life application of this redox chemistry. Some batteries, like the one in your mock assessment, are not able to be recharged because in doing so they get so hot that the electrolyte basically catches fire. Don't try it. But your little AA batteries that are not nickel cadmiums, for example, are not rechargeable because the ammonium chloride electrolyte will catch fire if you try to recharge them. A lot of batteries, though, like the ones in your cell phones, are called dry cells because they have no liquids in them. They've got gels, but no liquids in them. So their electrolyte is a gel, and they don't overheat to the level of catching fire anyway. So they are rechargeable. The most common one in everyday life, therefore, now would be the one in your cell phone. Okay, the ones in those are dry cells that can be recharged, basically. The other very common one is going to be our case study for today, which is the lead acid battery, because every vehicle basically uses these to get started and to run things like the clock and the radio and that sort of thing. So these are the batteries that provide the electricity or electrical energy for things in our vehicles, particularly to get them started, what's called the starter motor. That's called discharge when it's actually generating a voltage. And we need to understand, for this achievement standards criteria, we need to understand what's happening at the anode and the cathode. And we need to be able to think about what would we observe happening and how can we show that with equations and with electrode potentials. And that's what I've put up on the board for us. So we do not need to write a cell diagram for it. That's not part of our requirement. We'll either be given it or we just have to describe which one's the anode and which is the cathode, given electrode potentials for each of these things. Remembering that the one with the higher electrode potential will be reduced if it's spontaneous. It has to be spontaneous because when you turn the key in your scooter or your car or your motorbike, it turns the starter motor on. So it has to be spontaneous. So at the anode, we have got oxidation. We need to remember that. Of these two chemicals here, when we look at what they're paired up with, which is the lead ion, we know that this one must be the one being oxidized because this has got an oxidation number of 0 and this has got an oxidation number of 2. So this must be what happens at the anode for discharge. Therefore, lead dioxide must be what is being reduced at the cathode to generate this voltage. Interestingly, they both become lead 2+ ions, and they are dissolved in very concentrated sulfuric acid. So the lead ions very quickly precipitate out as lead sulfate. I just missed some states of matter there. However, for the actual redox reaction that is occurring, you don't need to worry about the precipitation. You need to worry about this overall reaction here because it is the combination of these two half equations. The next step of the chemistry is beyond what we need to know for the standard, but it is, I think, really worthwhile for knowing if you own a vehicle. It's making a deposit of lead sulfate. That lead sulfate will eventually coat the electrodes and stop the battery working. So if you get too much lead sulfate, so if you overuse the battery, then it's actually very, very hard to recover it, to recharge it. So that leads me to recharge. After we've created our 1.82 volts per cell, by the way, so there's 6 of these in a battery to create our minimum of 12 volts. It's after about 14.4 volts, I believe, is the ideal to get the starter motor going. During recharge, the anode is still the anode. The cathode is still the cathode. We don't change the names of them on you. But the reverse reactions are occurring. And these require at least 1.82 volts per cell, and there are 6 cells in a row. So the recharging needs at least that voltage to drive them, and these ones in reverse, so I have these reactions here. So now the opposite is occurring. The anode is now reduction. The cathode is now oxidation. So if I had a rechargeable battery in my assessment, and we have to give you a rechargeable battery in your assessment to meet the criteria, once you've got the anode and the cathode written out, don't change them about. Whatever chemicals were involved there, they're the same chemicals. You just need to flip, for recharge, you just need to flip the arrow around, basically. So if this can be reversed, how come we have to replace a battery? By the way, you don't have to do it often. In a motorbike, it's about every 15 years. So a scooter or motorbike, it's 15 years. They last a really long time. There's so few electrical parts in those. One is water, and that's really easy. You just top them up with water. As you're recharging the battery, it gets hot. And because it gets hot, and there's little vents in the top of the batteries, we lose water for evaporation. But as well as that, if you overcharge the battery, then what happens is the water molecules, there's an arrow, the water molecules split up, as you can do, this is what we're doing for redox. The water molecules split up into its ions, and the ions turn into the molecules. So we end up losing water as as the ions and then oxygen gas. So we lose water through electrolysis. Electrolysis is something I'm going to teach you next. I'll do that in more detail. We'll do that one. So we lose water. Easy to fix. We just top it up with water. In Christchurch, we're really lucky. Our water has so few impurities in it that we can just use tap water. In most parts of the world, you'd have to take it somewhere and get deionized water. We would have taken particularly the metal ions like calcium and so on out of the water. As I said before, lead sulfate. These lead ions combine with the sulfate of sulfuric acid to make lead sulfate, and they coat the electrodes. They actually cover the electrodes, and once they're covered, it can't conduct electricity anymore. And then, of course, every time you recharge a battery, you don't get all of those chemicals back. You get most of them back, but there's a little bit you don't get back. So over time, lots of rechargings, eventually those electrodes will corrode away. So to compare and contrast this, what would we observe at the anode and the cathode for discharge? Well, this is a dull grey metal, and this is not. This is at this stage an aqueous ion. It's dissolving away. So what I would notice is that I'd see very little, but if I was to weigh the anodes, it would be lighter. So there would be this being eaten away, eroded or corroded. Any of those words would be good to use. You might see the lead sulfate deposit, which would be white. But the key thing is that this would be being eaten away. This would get smaller, this anode. The cathode, same thing. It's going from being a solid to being something in solution initially. So again, the lead oxide would be eaten away. Lead dioxide would be eaten away. All right, so that's what we would observe is dark grey metal being eaten away. And here's one thing I didn't prep before doing the video. That's also a dark colour, so you'd have that being eaten away as well. Therefore, at recharge, what would we observe? We would observe that the anode is getting bigger, that there are deposits of the dark grey metal, that there are deposits of the lead oxide happening. Remember, in this assessment, you have to link observations to species. Right? And the nice thing is we give you the observations, you just have to go, oh, well, that's that being made. So if I've got my colours wrong in the video, I apologise. I'm pretty sure that's a dark colour as well. a dark grey colour as well. So, lead acid batteries, really good example of a rechargeable battery. You need to be able to say what's happening at the anode and cathode, relate it to any observations that I give you in the assessment, do an overall reaction, work out the electrode potential of each cell within that battery. You then need to compare and contrast that to what's happening for recharge. Those are the key things you need to go do in an assessment. You'd need to say the minimum voltage per cell required to recharge it as well. Any questions while I've still got this playing?